Hello everyone, welcome to Cloudcraft Podcast. I am your host George, and today we are breaking down the architecture of a critical security tool in modern cloud native defense. The title of today's episode says it all. Deep dive inside the kernel, threat detection with the AWS Security Agent and GuardDuty. Today we are focusing on resolving one of the most dangerous blind spots in modern cloud infrastructure, achieving real-time deep runtime visibility inside dynamically scaling container workloads. Consider a standard enterprise deployment. You have migrated your core transactional APIs onto Amazon Elastic Kubernetes Service. From a perimeter security standpoint, you have implemented defense in depth. Your clusters sit behind AWS WAF, VPC security groups restrict traffic, AWS CloudTrail monitors control plane API operations, and IAM roles for service accounts enforce the principle of least privilege. On paper, the architecture complies with organizational baselines. But let's analyze the operational reality. Suppose an application dependency contains a zero-day remote code execution vulnerability. An external adversary successfully exploits this flaw, establishing an active shell inside a running pod container namespace. At this precise moment, your standard cloud logging infrastructure goes blind. AWS CloudTrail cannot see inside the container. It tracks AWS API calls, not Linux binary execution. VPC flow logs will capture network packets, but they lack the application layer context to differentiate legitimate microservice traffic from an active exfiltration stream. If that adversary executes local privileged escalation, modify critical system binaries, or attempts a container escape to compromise the underlying EC2 worker node, your security operations center remains completely unaware until the damage is done. For industries bound by strict compliance framework such as financial technology handling PCI-DSS or healthcare subject to HIPAA, this visibility gap represents an unacceptable business risk. A single undetected runtime breach can culminate in multi-million dollar regulatory fines, catastrophic brand devaluation, and operational paralysis. The challenge we face as cloud architects is clear. How do we achieve deep runtime threat detection inside dynamically scaling containers without degrading application performance or introducing heavy third-party management overhead? The architectural answer to this problem is Amazon GuardDuty runtime monitoring, powered fundamentally by the managed AWS Security Agent. To understand why this solution is a paradigm shift, we must look past the AWS Management Console and examine how the security agent operates directly at the Linux operating system layer. Traditionally, monitoring runtime behavior required deploying heavy third-party agents as privileged demand sets inside your Kubernetes clusters, or running agent process directly on your virtual machine. These legacy tools typically relied on loading custom kernel modules or utilizing standard system tracing utilized like ptrace. The architectural drawbacks were several. Custom kernel modules risk destabilizing the host operating system when kernel updates occur, and tracing hooks introduce a non-trivial performance tax, intercepting and blocking system calls in the execution path. In a high throughput, low latency API environment, this performance penalty directly translates to increased latency and inflated compute bills. The AWS security agent circumvents this limitation entirely by leveraging eBPF, extended Berkeley packet filtering technology. For architects looking at the low-level mechanic, eBPF allows the security agent to run sandbox code directly inside the Linux kernel space safely and asynchronously. Instead of acting as a blocking proxy in the middle of a system call, the agent's eBPF probes act as a passive mirror. When a process inside a container namespace issues a system call, such as execve to execute a binary, open it at access a file, or connect to open network socket, the agent captures a copy of the telemetry event instantly. Because this code is verified by the kernel before execution, it cannot crash the operating system because it runs asynchronously. The security agent reads system telemetry without blocking the execution threads of your core application containers. Your financial or transactional APIs maintain their baseline throughput and latency profiles. From an engineering lifecycle perspective, AWS has abstracted the operational complexity of managing eBPF props through automated agent management. When enabled, GuardDuty interface directly with Amazon EKS to deploy the agent as a native cluster add-on. AWS handled the lifecycle, automated updates, and resource constraints of the agent demo. Furthermore, to maintain strict network isolation, the agent does not stream this highly sensitive telemetry over the public internet. Instead, AWS dynamically configure a managed VPC endpoint within your architecture, routing the eBPF system event securely through the AWS private network backbone into the GuardDuty threat intelligence engine. To demonstrate the real-world utility of this architecture, let us discuss an advanced multi-stage attack sequence targeting an EKS hosted environment and evaluate how the correlation engine handles the blast radius when the security agent is active. Imagine an adversary targeting our vulnerable payment processing pod. Let's look on remote code execution and outbound communication. If the adversary sends an exploit payload targeting the application layer, the application parses the request, triggering an RCE vulnerability. The hacker establishes a reverse shell, prompting the container to initiate an outbound network connection to an external command and control server to fetch a post-exploitation toolkit. At this point, GuardDuty's network layer protection triggers an alert. By continuously injecting VPC flow logs and Route 53 DNS query logs, GuardDuty recognizes that an internal IP address is communicating with a known malicious endpoint. However, at a network layer, that IP maps to the EKS worker node, not necessarily the specific microservice instance. So next, look on privilege escalation and container escape. With the toolkit downloaded, the adversary attempts a container escape. They execute a local exploit binary aimed at exploiting a vulnerability in the shared Linux kernel host, attempting to break out the container's isolated control groups and expenses to gain root privileges on the underlying EC2 host. This is where the eBPF layer proves its value. The AWS Security Agent immediately catches the anomalous excuse call, executing highly suspicious argument, combined with unexpected modification to host file systems via openat. The agent packages this telemetry and streams it to the GuardDuty backend. GuardDuty parses the event against its behavior-based threat models and issue a critical serverity runtime finding, execution runtime hash container escape. Now look on the credential access via IMDS. Now operating with root privilege on the host EC2 instance, the adversary targets AWS resource access. The query the instance metadata services IMDS v2. The extract the temporary IAM credential associated with the EC2 worker node's instance profile. Armed with this credential, the adversary attempts internal reconnaissance, executing commands to discover S3 buckets and IAM permission within the wider AWS account. The defense architecture counters these from two vectors simultaneously. The security agents maps the exact process ID, executing the local metadata queries. Concurrently, GuardDuty processes cloud trail management events using machine learning to detect that the node's IAM identity is suddenly generating anomalous API discovery traffic completely decoupled from its historical baseline. The next step is data exfiltration and AI correlation. Finally, the attacker locates an Amazon S3 bucket containing sensitive records and execute a mass synchronization command to exfiltrate the data. GuardDuty's S3 data plane protection flags the anomalous object access pattern. If this were a traditional siloed security environment, your incident response team would be full with four separate alerts: a network anomaly, a host file system alert, an IAM credential abuse alert, and a S3 exfiltration alert. Sorting through these logs to build a coherent story would take hours or days, expanding your mean time to resolution. Amazon GuardDuty solved this through its intelligent attack sequence feature, which relies heavily on the data fed by the agent. It ingests the eBPF's runtime telemetry from the security agent and correlates it deterministically with the CloudTrail, DNS, and VPC logs. Instead of four independent alerts, it generates a single unified contextual timeline. Alerts starting like a container escape occurred within EKS cluster name, the alpha here, namespace, production, port name, payment API 123B. The associate process ID extracted IMDS credential and used them to exfiltrate data from S3 bucket, customer payment records. Yeah, this provides the exact container image SHA, the namespace, the port, and the malicious command executed, allowing your incident response team to isolate the threat within seconds. Okay, as we wrap up today's deep dive episode, let's synthesize the strategic takeaways for cloud leaders and architects. First one, control plane visibility is no longer enough. Modern cloud native security demands deep runtime visibility inside the operating system and container namespace to defend against sophisticated code level exploits. The next one, leverage first party low overhead innovation. Utilize native technologies like eBPF via the AWS Security Agent to decouple security telemetry collection from application performance, ensuring protection doesn't degrade your user experience. Priorities alert context over injection volume. Shift your incident response paradigms towards service that provide intelligent event correlation, like GuardDuty attack sequence, to cut down log noise and empower your response with immediate actionable blast radius maps. If you are currently running production workloads on Amazon EKS, Amazon ECS, or Amazon EC2 without runtime level monitoring, your actionable next step is to evaluate this capability. Navigate to the Amazon GuardDuty console in a non-production account, enable runtime monitoring, and leverage automated agent management to review the telemetry footprint for yourself. To validate the low-level architectural components, eBPF specifications, please refer to the official AWS documentation for the up-to-date details. Thank you for joining me on CloudCrack Podcast. Implement defense in depth, design for predictability, and stay secure. Until next time, thank you.